Hi, this is Good Design Practices Part 2. In the last session, we learned how to improve code readability, how to use indentation in your VHDL code, how to avoid latches in the combinational circuits, and what are the good structures when you are working with the clock signals. We also learned that modern FPGA comes with many number of inbuilt registers, so feel free to use them in your designs. These can help you to enhance your timing performances of your designs. They can also simplify your debugging and verification processes as well. So try to use those registers for your input output ports in your VHDL designs. This is a simple block diagram of what I explained in the last slide. So you can see that your input and outputs are well synchronized with your clock signal. And by doing this, you will minimize your timing issues in your real hardware. Let me explain this. So we have this simple module. It has input A and output B, and of course, one clock signal. Now we are doing some operation on signal A using this logical implementation. And this can be anything depend on your project needs. And then we get the output at port B. But we didn't connect this output directly to the FPGA pin. Instead, we moved it through this flip-flop. Means your output is well synchronized with the clock signal. So it does not matter that what is your transition delay. You will get output only at the clock transition. As an additional step, we have also synchronized input ports as well. So before using this input, we passed it to this flip-flop. Means the output of this flip-flop is registered version of signal A. So your input signal is well synchronized with your system clock before further processing. This simple design practice can reduce your timing errors and help you to offer consistent and predictable behavior in different real life conditions like we discussed. And you will get a robust design which is well equipped for different situations. Now you may question that how this method improves your timing performance and how it make your design more robust against the real life conditions. So we will understand this with the concept of pipelining in the next slide. Pipelining is a concept to manage the data flow more efficiently at maximum possible operating frequency. So few points about pipelining is we know that larger combinational functions also have longer delays. So it creates timing bottleneck. So pipelining helps you to mitigate these delays and boost your timing performances. Pipelining uses extra registers to break up large combinational functions into a smaller one. Let's visualize this in a real life example. So we have this big combination circuit. Just assume this like any big circuit structure with lot of elements which are connected one after another. Means output of one element goes into the input of another component and further passes to more elements like this to the output. And finally reaching at the output like we have chat signal here. Now because there are a lot of components in this structure, so your input signals has to go through from these elements to reach at the output, right? Means they will have higher gate delay or propagation delay, anything you can say. And that delay is a major bottleneck in high speed circuit designs. So they can limit maximum speed of your FPGA designs, means your hardware performance will hit in terms of circuit delays. So question is that how you will minimize that delay or how you can increase timing performance of your designs. Well, one simple way is that just reduce the propagation delay, right? How? Well, try to use better fabrication process and design smaller elements, right? But the problem is that this process is costly in terms of chip development because you need newer technology for developing them and that come with the cost. Also, you do not have much control beyond some point because that has some limit. And if you're only working on the FPGA designs, then you do not have that choice as well. You can just choose a better FPGA model and that's it. And their performances is well known, means you cannot demand better from the same chip. So the option you have is to optimize your structure design itself, means your combination circuit. How? So the simple answer is by using pipelining. So in pipelining, we simply break a large combinational chain into a multiple shorter chains. Now you will have individual delay for each segment or each set of elements, which are splitted for smaller tasks. For example, suppose if this big structure has 10 nanosecond of delay in some specific condition. Now, when you break this, you will have smaller delays for each segment. Like some group will have 4 nanosecond, some will have 8 nanosecond, and some will have 6 nanosecond like that. Now, if you are clear that what is pipelining, then let's understand how it works and how it can help you in reducing overall timing performances. Now remember that we have used register version of input and output ports here. Do you see these flip-flops at input and output ports? Means they are synchronized with the clock signal. We discussed that in the last session, that why we are doing this. So our goal is that we are trying to improve that operating clock cycle for this design, right? So let's see how it is happening by pipelining. So here we have two timing diagram. Top one has the clock frequency of 50 megahertz and bottom one has the clock frequency of 100 megahertz. Now in the last slide, we assume that our propagation delay is 10 nanosecond, right? And for that big combination circuit. So 50 megahertz clock has 20 nanosecond of a clock cycle, right? And 100 megahertz clock has 10 nanosecond of clock cycle. Means 50 megahertz signal will take 20 nanosecond to complete one cycle and 100 megahertz will take 10 nanosecond to complete one cycle. This is a simple math. Just divide your clock frequency from 1 second and you will get the time for a one clock cycle. Like 1 second divided by 50 megahertz, then it is 20 nanosecond. And same 1 second divided by 100 megahertz, then you will get 10 nanosecond, right? Now remember that what was our propagation delay for that circuit? That was 10 nanosecond, right? Means we cannot use more than 100 megahertz signal for that design. If you use it, then your design will malfunction because your signal transactions will not happen before the cutoff time. So 100 megahertz is your maximum operating frequency for your design. And now the task is to improve it. But before that, let's understand these two timing diagrams. Because if you do not understand this, you will not understand next slide as well. So first focus on this 50 megahertz signal. Suppose we changed our input at this point. Now because your circuit has 10 nanosecond delay, so your output will change at this point, means after 10 nanosecond. So after this point, whenever you get the rising edge of your clock, you will get your final output and that will be your correct output. Remember that final output is driven by a flip-flop and synchronized with the clock rising edge. Means you will get correct output at the rising edge of this frequency. Now let's do the same for the bottom timing diagram. This has 100 megahertz of a clock cycle. Means your clock has 10 nanosecond of cycle. Now if you change your inputs at this point, your output will still change after 10 nanosecond because that is your propagation delay, right? So after this point, your output will be captured by the flip-flop and you will get your final output. Means if anything change beyond this point, then your output will not change at this clock cycle. It will need another rising edge of your clock, means another 10 nanosecond. So this 100 megahertz frequency can also work fine because your output become valid just before the rising edge of your clock cycle. Although it is very neck to neck, hence this is not recommended because slight external changes can fail your system. Also, your flip-flop will also need some setup time So there is a possibility that your flip-flop will not capture signal on time due to very tight timing constraint. So in short, 50 MHz is a perfect fit for this design and 100 MHz is acceptable but not recommended. Now here is the actual problem comes when you increase your operating frequency to 120 MHz. So look at this bottom timing diagram. This is for 120 MHz clock signal and top one is copied from the last slide and it is for 100 MHz clock signal. So let's focus on the bottom one this time. When clock is 120 MHz means clock period is 8.3 nanosecond, but your design still have 10 nanosecond of propagation delay. So you can see that this is our clock cycle and we get the rising edge at 8.3 nanosecond and we change our inputs at this point. So we get our output after 10 nanosecond. But the problem is that at this point, when clock signal having the rising edge, you still do not have the valid output because it takes 10 nanosecond. So you will get the right output at this point. So as a consequence, your output is not correct at this point. Means you cannot use this frequency for your circuit because you will not get a reliable output from your designs at 120 megahertz. So let's see if pipelining can help you to improve this situation. Now, by implementing the pipelining, we divided the large combination logic into two or more smaller segments of combination circuit. This division will help us to manage delay more effectively. Now, what we have did that we break down our big circuit structure into two separate designs and we inserted additional flip-flop between these two designs or segment you can say. This we called pipelining concept and your propagation delay is now reduced for each individual segment. So in this case, your highest propagation delay is 6 nanosecond for one segment. And now this can drive your more operating frequency. Means highest delay reduced from 10 nanosecond to 6 nanosecond. Although the total delay is still 10 nanosecond, but segment delay is splitted in 6 nanosecond and 4 nanosecond. So don't get confused. But the benefit is that this flip-flop, which is in between, will capture your signal according to the 6 nanosecond delay. And then it will forward that to the next segment. So if we consider to neck operation like 100 megahertz with 10 nanosecond delay, now it become 160 megahertz with 6 nanosecond delay for the same design. Means your operating frequency is increased from 100 megahertz to 160 megahertz. If you break down your big structure into and insert additional flip-flops between them as bridges. So this is called pipelining concept. So we understand it, right? But there is a trade-off. If you are using pipelining, you know what? Although we increased our operating frequency, but now you will need additional clock cycle to get your final output. And of course, additional flip-flop elements in your hardware. So this is the downside of this approach. But at least you get the right results and your designs is not malfunctioning. And that is more important, right? So quick brief, always try to use synchronous systems for your designs like we did for our input output ports in the last example. Means you will have one clock signal which is driving all the flip-flops and everything else is synced with your clock signal. Ensure your input and outputs are properly synced and by doing this you can eliminate maximum of your timing issues in your designs. Means lesser timing glitches and errors compared to a asynchronous design. Means better FPGA designs covering more practical situations, right? Try to prefer registered process blocks over conventional process block and it will enhance the reliability and performance of your designs. Also, synchronous designs are easier to debug and maintain, so they are more practical for complex FPGA projects. So quick summary that what we have covered till now in the best practices. First, always use meaningful names and proper indentation to enhance your code readability and maintainability. And by doing this, your code appear more professional and self-explanatory. Next is avoid using latches as they can cause timing issues and lead to the unreliable circuit behaviors. Fourth is do not generate clocks using logics. They can affect your design performances. So use PLLs or phased lock loops to modify clocks. Don't add circuit elements on the clock path. Instead, write your code for the data path, like we discussed about multiplexer example for the enable pin functionality. Use registered or flip-flops in your designs for better timing performances. Apply pipelining concept whenever you are required higher operating frequency. Try to design synchronous circuits instead combinational circuits for better reliability and performances. In the next session, we will continue with more tips and tricks to make your VHDL designs more agile and flexible and more reliable at the same time. So stay tuned for the updates. If you did not subscribe till now, then please do subscribe to learn and grow community for regular updates. If this video is informative, then please like this video, comment on video, and don't forget to share. Thank you for watching.